Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12 physics get more than 95% marks series. Chapter is alternating current, chapter 7 ncert line by line part 3. If you have not subscribed our channel, we request you to subscribe it as soon as possible. Please like our videos and share them among your friends and relatives so that they can also get benefit of these YouTube lessons. Please click on the bell icon to get automatic notification whenever a new video is uploaded by us so that you should not miss any of our important video tutorials. Let us begin today's lesson. Today we'll start with Section 7.5 AC voltage applied to a capacitor. Figure 7.8 shows an AC source E generating AC voltage V is equal to Vm sin omega t connected to a capacitor, a purely capacitive AC circuit. When a capacitor is connected to a voltage source in a DC circuit, current will flow for the short time required to charge the capacitor. As capacitor accumulate on the as charge accumulate on the capacitor plates, the voltage across them increases, opposing the current. That is, a capacitor in a DC circuit will limit or oppose the current as it's charged. When the capacitor is fully charged, the current in the circuit falls to zero. This happens in a DC circuit. When the capacitor is connected to an AC source, as in figure 7.8, it limits or regulates the current but does not completely prevent the flow of charge. The capacitor is alternately charged and discharged as the current reverses each half cycle. Let Q be the charge on the capacitor at any time t. The instantaneous voltage V across the capacitor V is equal to Q by C. Equation 7.15. Let us derive the expression separately in a easy way. So Vm V is equal to Vm sin omega t. This is the potential difference applied in a is by the AC source to a capacitor in the circuit. So this is the circuit, this is the capacitor, and here is the AC source. Now the potential difference between the capacitor is Q by C, and this we have learned in electrostatics chapter. So this is given as 7.15 as in the book. So applying the Kirchhoff's loop rule, the voltage across the source and the capacitor is equal. So according to Kirchhoff's loop rule, the voltage across the source and capacitor is equal. The voltage across the source and capacitor are equal. So we can write Vm sine omega t is equal to Q by C. To find out the current, we use the relation. So we know I is equal to dq by dt. Why? Because the rate of flow of charge is known as electric current. So I is equal to, so if we differentiate the charge with respect to time, we get the current. Now I is equal to d upon dt bracket Vm C sine omega t. Here we have to understand what we have done. So from this equation we can write, so which implies that Q is equal to Vm C sine omega t. So Q's value, what we have done, put the Q's value here, dq by dt. So Q's value you have put here. Now upon differentiation, what we get, I is equal to, if we differentiate Vmc sine omega t, will get Vm cos omega t, and if we differentiate omega t with respect to dt, will get omega. So ultimately omega c Vm and cos omega t, omega t. This is normal differentiation. Now we got the value of I here using the relation. So now we know that from trigonometry, using the relation cos omega t is equal to sine omega t plus pi by 2. We will use this relation here, and we can write I is equal to Im sine omega t plus pi by 2. This is equation number 7.16 from your book, where Im is equal to where Im is equal to omega c Vm. So what we have done, instead of cos omega t, we have put this, and and instead of this whole thing we have written Im, and we derived here to this equation. uh, Im sine omega t plus pi by 2, where Im is equal to Vc Vm. Next, again we can rewrite the equation Im is equal to Vm upon 1 upon omega c. So same equation we can rewrite as this. Now now comparing it with Im is equal to Vm upon R for purely resistive circuit, we find that 1 by omega c plays the role of resistance. So this plays the role of resistance. Now it is called capacitive resistance and it is denoted by Xc. So we won't write it R, we write it as Xc, capacitive resistance. So we can write Im, so we can write Im is equal to Xc is equal to 1 upon omega c. So that amplitude of the current is, therefore we can write the amplitude of the current of the current is Im is equal to Vm upon Xc. That is equation number 7.18. Next, this is the equation 7.18 which is given in your book. Now let us see the book. So we have derived the equation 7.18. Now let us see this graph and try to understand what it is. In figure 7.9a, a Phasor graph for the circuit in figure 7.8, and B, graph of V and I versus omega t. So the dimension of the capacitive resistance is the same as the resistance and its SI unit is ohm. So capacitive resistance is same as resistance and is the dimension is same as resistance and its unit is ohm. The capacitive resistance limits the amplitude of the of the current in a pure capacitive circuit in the same way as the resistance limits the current in a pure resistive circuit, but it is inversely proportional to the frequency and the capacitance. Remember, so capacitive resistance is inversely proportional to the frequency and capacitance. Why? Because xc is equal to, why we are saying that, because xc is equal to 1 by omega c, 1 by omega c. So it is inversely proportional to the frequency as well as to the capacitance. A comparison of equation 7.16 with the equation of the source voltage, that is 7.1, shows that the current is pi by 2 ahead of voltage. So in this case, current is pi by 2 ahead of voltage. Figure 7.9a shows the phasor diagram as at instance t1. Here the current phasor I is pi by 2 ahead of voltage phasor V. As rotate anticlockwise. Figure 7.9b shows the variation of voltage and current with time. We see that the current reaches its maximum value earlier than the voltage by 1/4 of a period. The instantaneous power supplied to the capacitor is Pc is equal to IV, that is, we will put the value of I, that is Im cos omega t, and we'll put the value of V here, Vm sin omega t. So how we got this? I will I will be written as Im cos omega t. V will be written as Bm cos omega t. So ultimately, if we multiply it, Im Vm cos omega t sin omega t, divide by 2, divide and multiply by 2. So it will get divide and multiply by 2. So we'll get 2 sin omega t cos omega t. We can write 2 sin omega t cos omega t. We can write sin 2 omega t. Why? According to the trigonometry, 2 sin a cos a is equal to sin 2a, and this upon 2 comes here. So ultimately the equation converts to Im Vm sin 2 omega t upon 2. This is equation 7.19. So as in the case of inductor, the average power Pc is equal to Im Vm sin 2 omega t upon 2 is equal to Im Vm upon 2 sin 2 omega t, mean of sin 2 omega t, which is equal to 0. Since sin 2 omega t is equal to 0 over a complete cycle, figure 7.10 explains it in detail. Thus, we see the case of an inductor, the current lags the voltage by pi by 2, and in case of capacitor the current leads the voltage. This, in case of capacitor, it is opposite, current leads the voltage by pi by 2. Now let us see few examples. A lamp is connected with in series with a capacitor. Predict your observation for DC and AC connections. What happens in each case if the capacitor if the capacitance of the capacitor is reduced. When a DC answer is when a DC source is connected to a capacitor, the capacitor get charged and after charging no current flows after it is full charge, not charging, full charge. No current flows in the circuit and the lamp will not glow. There will be no charge even if C is reduced. So in that case, there will be no charge even if the C is reduced. This is about AC source. Now, this is about DC source. Now, with AC source, the capacitor offers capacitive resistance of 1 upon omega C and the current flows in the circuit. Cons con Consequently, the lamp will shine. Reducing C will increase the resistance and the lamp will shine less brighter than before. So this is but in no case the lamp will not glow. So this is the difference when a lamp is connected in series with a DC source and a DC source and a AC source. Now the next question, example 7.4, a a 15 microfarad capacitor is connected to a 220 volt 50 Hz source. Find the capacitive resistance and current RMS and peak in the circuit. The frequency is doubled. If the frequency is doubled, what happened to the capacitive resistance and the current? The capacitive resistance is Xc is equal to 1 by, so Xc is equal to 1 by omega C. We know that. Omega is equal to 2 pi nu. So Xc is equal to 1 by 2 pi nu C. So we'll put this value here instead of omega and we got 2 pi nu C. So here we have written this formula and put the value, all the known values, we get the value of capacitive resistance, that is Xc. The RMS current is I is equal to V upon Xc. So put the value of V and Xc. Xc we have found out in the first uh, A part. So we got the I is equal to 1.04 A. The peak value, the peak current is Im is equal to root 2 I, that is root 2's value is 1.414 and I's value we have just find out I's value, and putting this value we get the value as peak value of current as 1.47 ampere. This current oscillates between plus 1.47 and minus 1.47 ampere and is ahead of voltage by pi by 2. Why? Because it is the normal phenomenon when a capacitor is added in series in a AC source to a AC source, current is always ahead of the voltage by pi by 2. If the frequency is doubled, the capacitive resistance is halved and consequently the current is doubled. Why? Because capacitive resistance is inversely proportional to the capacitance and inversely proportional to the frequency. If the frequency is halved, so frequency is doubled. So if the frequency is doubled, so instead of W, now it is 2W. Then what will happen? Of 1 by omega c we can write xc. So x dash c will be xc upon 2. If the frequency is doubled, then then this is halved, xc by 2. X dash c is equal to xc. So it is halved. It is halved. Now the current is doubled. Again, current is equal to why the current is doubled? Current is equal to V by xc. Now since xc is halved, so this 2 will go multiply here in the numerator and the current will be doubled. So what we can write, I dash is equal to 2V by xc. So V by xc we can write 2I. So I dash is equal to 2I. I dash is equal to 2I. The current is doubled. Now let us see example 7.5. A light bulb and an open coil inductor are connected to an AC source through a key as shown in the figure 7.11. So here is the figure. The switch is closed and after some time an iron rod is inserted into the interior of the inductor. The glow of light bulb A increase, B decrease, C is unchanged as the iron rod is inserted. Give your answer with reasons. Solution. As the iron rod inserted, the magnetic field inside the coil magnetized the iron increasing the magnetic field inside it. Hence, the induce or induction of the coil increases. Consequently, inductive resistance of the coil increases. As a result, a large fraction of the applied AC voltage appears across the inductor, leaving less voltage across the bulb. Therefore, the glow of the light bulb decreases. So now we will do this part. These are the different scenarios. So we'll do one by one. The current I flows as shown and from the maximum at 0 reaches to 0 value at 1. The plate A is charged to positive polarity while negative charge Q builds up in B, reaching a maximum at 1 unit. The current becomes 0. The voltage Vc is equal to Q by C is in phase with Q and reaches maximum value at I. Current and voltage are both positive. So P is equal to Vc, T is positive. Energy is absorbed from the source during the quarter cycle as the capacitor is charged. So here the main thing is energy is absorbed from the source during the quarter cycle as the capacitor is charged. This is the important thing. In part 2 what happens? So let us again go through the part 1. The current I flows as shown in the and from maximum at 0 and from the maximum at 0 reaches a zero value at 1. The plate A charged to positive polarity while negative charge Q builds up in B, reaching at maximum at 1 until the current becomes 0. So initially plate A is positively charged and plate B is negatively charged. Now the voltage Vc is equal to Q by C is a phase with Q and reaches maximum value at 1. Current and voltage both are positive. So P is equal to power is equal to Vc multiplied by T is positive. Energy is absorbed from the source during the quarter cycle as the capacitor is charged. It is self-explanatory. Now the second part, the current I reverse its direction. Now what happens? The current was flowing in this direction. Now it is flowing in this direction. Reverse this direction. What will happen then? The accumulated charge is depleted. That is, the capacitor discharged during the quarter cycle. The voltage gets reduced but is still positive. The current is negative. Their product, the power is negative. The energy absorbed during the 1/4 circle cycle 0 to 1 is reduced during this quarter. Now in the graph we see in the 0 to 1 what happens, it is charged. In 1 to 2 it is negative and it is discharged. Again 0 to 1 it is charged. Again 2 to 3 it is charged and 3 to 4 it is discharged. One complete cycle of voltage current. This shows one complete cycle of voltage current. Note that the current leads the voltage. Here current leads the voltage by pi by 2. Remember. In 2 to 3, I continues to flow from A to B. The capacitor is charged to reverse polarity, that is, the plate B acquires positive and plate A acquires negative charge. Both the current and voltage are negative, therefore, the product P is positive. The capacitor absorbs energy during 1/4 cycle. In 3 to 4, what happens? The current I reverses its direction at 3 and flows from B to A. The accumulated charge is depleted and the magnitude of voltage Vc is reduced. Vc becomes 0 at 4 when the capacitor is fully discharged. The power is negative. Energy absorbed during 3 to 4 is returned to the source. Net energy absorbed is 0. And these are the four conditions, four half cycles explained. Now the next topic, 7.6, AC voltage applied to a series LCR circuit, will do in the next class. So let us review what we have done today. Today we have started with 7.5, AC voltage applied to a capacitor, and we have found the different derivations for uh, amplitude, current, etc., power, and we have solved few sums with these concepts. We have seen different conditions, different in graphical conditions, 1/4 of the cycle, quarter cycle in the graph, as well as the explanation for it. So this is the first quarter cycle, this is the second quarter cycle, and This is the third one, third quarter cycle, and this is the fourth quarter cycle. And in the graph we have seen in totality of all the four quarter cycles what happens when it is charged, when it is discharged, etc. We have solved few numericals, and this was the end of today's session. Before closing our session, we request you to subscribe our channel if you have not done yet. Please like and share our videos among all of your known friends and relatives. Please click on the bell icon so that you can get automatic notification whenever a new video is uploaded by us, so that you will not miss any of the important videos. Thank you very much for supporting us and watching our videos.